So, let me give you an underdefined version of the algorithm. Okay, so it takes an array A of length n, looking for the ith order statistic. So as always, there's a base case for one element arrays. So what's the idea? You choose a pick somehow. Okay, and for the moment, I am not going to tell you how we. This is just defined in some arbitrary way. Okay, but it takes the array A and returns one of its elements. Then the next thing you do is you partition the array. Around this chosen key. Now, suppose that after you partition around P and the pivot winds up in its rightful position, it's the jth of the array B. The picture I want you to have in mind is this one. So this is a B here. So the pivot winds up somewhere. In index j, where j could be anything between 1 and n. We're going to call this the first part of B. We're going to call this the second part of B. Okay, it is in neither part. And so now we got to get the recursion right. Okay, so this is the last step of the high-level version of the algorithm. We just have to figure out how to recur. So remember, we're looking for the ith order statistic. Okay, and remember, j is the position in which this pivot winds up. So in this case, what if this pivot winds up in the ith position?
Then you're done.
Then we're done, right? Because what's in the ith position? Remember, it's in the rightful position in the sorted array. It's bigger than exactly j minus 1 elements. So if I equals j, it's the ith order statistic, what we wanted in the first place. All right, but what if, that's probably not going to happen too often. So let's deal with the other cases. What if the pivot than what we're looking for? Okay, so it's actually the jth order statistic for j bigger than I. We got to recurse. What do we recurse on? Which side? First side. All right, we're looking for the I smallest element. The first contains the j minus 1 smallest element, and j is bigger than I. Okay, so I is in there somewhere. So return. Select on the first part, what's the sorry, let me rewrite that. J minus 1. And what order statistic are we looking for in the first part? So we were looking for the smallest in the entire input array A. This first part has the j minus 1 smallest ones overall. So what are we looking for from amongst them? The ith smallest, exactly. Okay, we've thrown out big stuff. We haven't smaller than what we're looking for, so we're still looking for the ith smallest. Final case. It comes back too small. Okay, we want the ith order statistic, and we found the jth one for j less than I. What side do we recurse on? Second part. And what's the length of that array? N minus j. We've thrown out the statistic do we want? I minus j. The ith smallest element. We've thrown out the jth smallest ones, so we want the I minus jth smallest of what remains. Okay. right, so we only recurse on smaller subproblems, so this is going to terminate, that's good. And it's also going to terminate correctly, okay? And I'm not going to make a big deal of this in lecture. It's not the best use of the lecture time. There is a complete, rigorous argument in the handout. It's just a paragraph. I think you should read it, okay? Introduction. But read it and make sure you could do these straightforward inductions yourself. Okay? And indeed, the way I wrote it in the handout, again, it's meant if you wonder what we're looking for when we ask you to prove that your divide and conquer algorithm is correct, we're looking something of the nature of that paragraph in handout number 6. So feel free to use that as a template for your own homeworks. Again, it's not the best, so I won't do it here. As a template, if you like, in your own divide and conquer correctness proofs. So that's not what's interesting about selection. Okay, correctness is not what's interesting generally about divide and conquer algorithms. As we've seen, what's interesting is understanding the running time over the entire course of the algorithm and all of its recursive calls. So what do you think? What can we say about the running time of this? Can we say much about it? What do you think? I really told you the whole algorithm, right? So you'd be justified in complaining that I left step 1 kind of undefined. Well, maybe we could just analyze the running time of this algorithm without even worrying about the guts of the choose pivot subroutine. What do you think?
You always say something like order of choose pivot plus and then keep going.
Okay.
It turns out the choose pivot is really bad. You know, my choose pivot, but it's fast. Then it'll be whatever the rest of the algorithm is.
That's a good point. So one point is that it depends how much work we do inside of choose pivot. Okay, so having not told you that, you don't know if choose pivot has a constant time of implementation, or time of implementation, or what. That's the point. Actually, another issue as well. I promised you that choose pivot was, say, constant time. Okay, it won't be for us, but I suppose I promised you that. Yeah. Say it again?
Their worst case would be like if you choose pivot, like in the front of the element all the time, it's going to turn you into the third.
Right.
And something in the front all the time, then you still have to look at the rest of the elements of the array like all the time. So you will only kill off like one element each time you double take.
Right. The point that you're making is, what did we say was cruel about partitioning? We said you make progress. You get to throw out one of the 2 subproblems. Well, you know, you might have intuition that the running time of this recursive algorithm is going, especially after the master method discussion, is going to be governed by not just whether we make progress at all, but how rapidly we make progress throwing out part of the array. So if we only throw out one element and we one elements, that's maybe going to be slower than if we succeed in throwing out, say, half, recursing on only half of the array. Okay? It's going to matter, in addition to the time spent in choose pivot, in some sense, how well choose pivot does its job of making progress, of dividing into reasonably equal subproblems, one of which we can throw out. So the upshot, the running depends on choose pivot. And not just the time done inside choose pivot, but in particular if we make bad pivot choices, and as was suggested, a really bad pivot choice would be something in which after you partition n-1, so bad pivot will make this algorithm run slow, and I suggest that you check that there are even cases in which a sequence of terrible pivot choices could make this run even in quadratic time. Okay? And remember, in this context, quadratic time is pathetic. We had a really, really easy n log n algorithm to solve the problem. Okay? So check. So if you are really unlucky or really make bad choices with the pivots, it could be omega of n squared. So remember, omega is the lower bound version of big O notation. Okay? So if we want this to run, to be competitive, or perhaps even superior to the merge sort solution, we have to make sure, we have to say something about the quality of our pivots. Okay, we need to ensure that they're good pivots. All right? And what makes a good pivot? Well, we want a reasonably balanced split. So what would be the king of all pivots? The optimal pivot would be the median. Split it exactly into two 50-50 pieces. So no matter which side we recurse on, we succeed in throwing out half of the array.
Would it always be median? I'm finding that later on in the array, wouldn't it be an element that's closer to that later element in the array or earlier element in the array? Is that what you're looking for?
So that depends. So so it is a more subtle in the following way, is you might get really lucky and maybe you get a 20 split, some kind of crappy split, but then it just turns out you get to recurse on the 20% side. And that would be really awesome. Then you throw out more than half the array. We don't count on that. Okay, you'd have to be a little lucky on the smaller side. So what we really want is we want to throw that no matter what, no matter which side we recurse on, we're going to throw out half. Okay, so that's really the holy grail here. All right. So again, to summarize, the best pivot, in the sense I discussed, would be the median, but that's what we're trying to compute, or that's perhaps what we're trying to compute. So this is really seems like an uninteresting observation. Okay, so this seems circular, but we can salvage the second and final really good idea in this algorithm from this observation, which is, well, we're not going to work so hard as to find the median, but we'll find a reasonable approximation of the median really quickly. Okay, so something that's at least as close as good enough to the median so that we get basically a constant factor progress every step. All right? So the goal is to find a pretty good pivot, not a perfect pivot, but in a precise sense, a pretty good pivot very quickly.